In this session, we will preview the Telecommunications and Network Security domain. The Telecommunications and Network Security domain encompasses the structures, transmission methods, transport formats, and security measures used to provide integrity, availability, authentication, and confidentiality for transmissions over private and public communications, networks, and media. In today's global marketplace, the ability to communicate with others is a mandatory requirement. A CISSP is expected to demonstrate an understanding of the communications and network security as it relates to data and voice communication. As with all domains, I will provide this preview in the context of the three principles of security: confidentiality, integrity, and availability, more commonly referred to as CIA. No other domain has the attention of management and users as the telecommunications and network security domain, especially in the realm of availability. It is common to hear of systems requiring 4 nines or even 5 nines of availability, where an outage of even seconds per month is serious. The movement towards greater deployment of voice over IP will create even more pressure on the availability of networks. In corporate networks, availability of services is commonly the key business requirement. For this very reason, network availability has also become a prime target for attackers and a key business risk. The easiest attack to carry out against the network, or so it may seem, is to overload the network through excessive traffic. Overloading the victim's network using a network or botnet of compromised machines that will launch an attack on command will allow the attacker to quickly overwhelm the victim's system. Don't let that victim be your organization. The integrity and protection of data in transit is a critical element of successful business and e-commerce transactions. Transmitted data must be sent to the correct location and not contain errors. A network needs to support the integrity of its traffic. Often, the same controls that provide confidentiality also provide protection of the integrity of a message. While the modification of messages will often happen at the higher network layers, networks can be set up to provide robustness or resilience against interception and change of a message or replay attacks. Networks, especially wireless networks, are particularly vulnerable to sniffing, so the protection of sensitive data in transit from disclosure is important. Various network protocols are needed for that purpose. The network is the carrier of almost all digital information within a corporation and therefore provides an attractive target to an attacker to capture information while it is in transit. Among the information that can be acquired are log-on credentials such as passwords and sensitive data within email contents. In some cases, an attacker might be interested simply in the fact that communication has occurred between two parties. This could lead to an inference attack. Our preview will focus on 4 main areas of this domain: the OSI model and TCP/IP protocols, network attacks, network devices, and network communications. Section 1: OSI model and TCP/IP protocols. The Open Systems Interconnect, or OSI model, was defined in 1984 and published as an international standard, ISO IEC 7498-1. The last revision to the standard was in 1994. While sometimes considered complex, this 7-layer model provides a practical and widely accepted way to describe network engineering. In practice, some layers have proven to be less crucial to operations, such as the presentation layer, while others, such as the network layer, have required more specific structure. There are several applications that overlap and transgress layer boundaries. The model has 2 major strengths. 1, it is established, widely accepted model. 2, it is flexible and generic. And, of course, with strengths, there are weaknesses. They are: 1, the model is generally considered complex, and 2, layer definitions are too coarse on the lower layers and too detailed on the upper layers. The CISSP candidate should have a general idea of what responsibilities of networking are addressed at each layer, and he or she should be able to name some practical protocols that address those responsibilities. When an application transmits data over a network, the data enters the top layer and moves to each successive lower level, moving down the stack until it is transmitted over the network at layer 1. The remote host receives the data at layer 1 and moves it to successive higher levels, moving up the stack until it reaches layer 7 and then to the host's application. It is important to see how this works. Layer 3 on host 1, for instance, communicates with layer 3 on host 2, but in doing so encapsulates the information it is passing to layer 3 on the remote host. Layer 3 on both hosts will communicate with layer 2 and possibly with layer 4. Each layer is defined so that it interacts either with its corresponding layer on the remote host or with the adjacent layers on the same host. To transmit data across a layered network, data is passed from the host application to a protocol on the protocol stack. Each protocol on the stack processes the data, encapsulates it, and then passes the data to the next lower protocol on the stack. Another reference model that information system security professionals should be familiar with is the Transmission Control Protocol / Internet Protocol, or TCP/IP model. It is very similar to the OSI model, but with a simpler structure. As the name implies, the TCP/IP model is designed to describe the TCP/IP stack. As with the OSI model, data that is transmitted on the network enters the top of the stack, and each layer, with the exception of the physical layer, encapsulates information for its peer. It places information at the beginning and sometimes the end of the message that it receives from the next highest layer. On the remote host, each layer removes the information that is peer encapsulated before the remote layer passes the message up to the next higher layer. Also, each layer processes messages in a modular fashion without concern about how the other layers on the same host processes the message. A CISSP candidate should know how the TCP/IP model maps to the OSI model. With that knowledge, the candidate should have a quasi-accurate understanding of what is happening within the 4 layers of the TCP/IP model. By briefly explaining the OSI model layers, you can use the mapping between the models to understand the TCP/IP layers. Layer 7, Application Layer, describes the structure, interpretation, and handling of information. Layer 6, Presentation Layer, describes the presentation of information, doing syntax conversions such as ASCII to EBCDIC and vice versa. Layer 5, Session Layer, describes the handshake between applications, such as the authentication and sign-on process. Layer 4, Transport Layer, describes data transfer between applications, provides flow control, error detection and correction using protocols such as TCP and UDP. Layer 3, Network Layer, describes data transfer between networks using protocols such as the Internet Protocol, IP. Layer 2, Data Link Layer, describes data transfer between machines, for example, by an Ethernet connection. And Layer 1, Physical Layer, describes the networking hardware such as network interfaces and cabling, and the way to transmit bits and bytes of data, whether as electrical pulses, radio waves, or light. Section 2, Network Attacks. Network security encompasses the structures, transmission methods, transport formats, and security measures used to provide integrity, availability, authentication, and confidentiality for transmissions over private and public communications networks and media. As always in IT security, the primary objectives are preservation and protection of confidentiality, integrity, and availability. However, the network as the central communications medium in most organizations has a special role to play in this, due to its role as the backbone of the technical infrastructure as well as its own technical complexity. A CISSP should know the types of attacks that pertain to the various models such as TCP/IP and OSI, and the layers within each model. These attacks are designed to permit an attacker to gain access to the network, launch some form of unauthorized activity, and perhaps use the network to attack systems or applications connected to the network. A CISSP should also understand the various steps that can be taken to prevent, detect, and respond to an attack. A discovery scan can be performed using very simple methods. For instance, by sending a ping packet to every address in a subnet. More sophisticated methods will also discover the operating system and services of a responding device. A compliance scan can be performed through the network or directly on a device, like in the instance of a security health check. If performed on the network, it will usually include testing for open ports and services on the devices connected to the network. A vulnerability scan can either test for vulnerable conditions or try an active exploitation of a vulnerability. A vulnerability scan can be performed in a non-disruptive manner. However, there is the risk that even a test for certain vulnerabilities might affect the target's availability or performance. Security attacks have been described formally as attack tree models. Attack trees are based upon the goal of the attacker, the risk to the defender, and the vulnerabilities of the defense systems. This is a specialized form of decision tree that can be used to formally evaluate system security. Target acquisition creates a list of possible targets and is often accomplished by evaluating directory services and network scanning. It is a means of intelligence gathering. The countermeasures are to limit the amount of information available on and about your network and attempt to distract the would-be attacker. An example, the use of honeypots. In the second step of an attack, target analysis, the identified target is analyzed for security weaknesses that would allow the attacker to obtain access. While the only real protection is to not allow security vulnerabilities in the first place, target analysis can be made more difficult for the attacker by removing any information identifying system type, build, and release. In the next step, target access, an attacker will launch an attack using the data they have gained to achieve unauthorized access. This can be accessed as a normal user or as a guest. The attacker may use common tools that exploit known vulnerabilities or bypass technical security controls altogether by using social engineering attacks. As a means of protection from this phase of attack, user privileges need to be managed, access profiles be up to date, and unused accounts removed. In addition, access should be monitored and monitoring logs need to be analyzed regularly. As the second level of an attack, the attacker will then seek to escalate his or her privileges on the system in order to gain system-level access permissions. Again, exploitation of known vulnerabilities through existing tools and techniques is the main technical attack vector. However, other attack vectors, such as the risk of an attack using social engineering, need to be considered. The use of host-based intrusion detection systems is an effective control that cannot be easily bypassed by the attacker and can provide detection of unauthorized changes to the system. Section 3. Network devices. The network topology defines which devices are crucial to network security, whether there are single points of failure, and whether controls are properly located. In a bus topology, all nodes transmit directly on the central bus. Each node listens to all of the traffic on the bus and processes only the traffic that is destined for it. This topology relies on the data link layer to determine when a node can transmit a frame on the bus without colliding with another frame that is on the bus. The bus topology has the single point of failure as the cable. In a tree topology, devices connect to a branch on the network, often through a switch, instead of being connected to a central bus. A cable or switch failure will cut off a branch of the tree, causing loss of connectivity for all the nodes downstream from that point of failure. In the ring topology, data is transmitted in one direction. Each device receives data from its upstream neighbor only and transmits data to its downstream neighbor only. Typically, rings use coaxial or fiber optics cables. Since rings use tokens to control traffic flow, the flow's rate is stable, and one can predict the maximum time that a node must wait before it can transmit. Thus, this type of topology is considered deterministic. Simple rings have a single point of failure. If one node fails, the entire ring fails. Some rings, such as Fiber Distributed Data Interface, FDDI, use dual rings for failover. In the star topology, each node is connected directly to a central device, such as a hub, switch, or router. Modern LANs usually employ a star topology because it's considered more scalable and manageable. The failure of any nodes or cable to a node will not affect the rest of the network. A star network is very flexible, and it is simple to add or remove nodes as needed. Nevertheless, the central device is a single point of failure. The answer to each topology's single point of failure is a mesh topology. In a mesh network, all nodes are connected to every node on the network. A full mesh network is usually too expensive because it requires many connections. As an alternative, a partial mesh can be employed in which only selected nodes are connected in a full mesh and the remaining nodes are connected to a few devices. Mesh networks provide a high level of redundancy. The failure of any node or combination of nodes or cable links will not affect the operations of the remainder of the network. The disadvantages are that they are complex and expensive. No matter what the topology, some common devices are hubs, switches, routers, and gateways. A hub is a multi-port repeater that retransmits a signal that is received on one port. Switches are similar to hubs, but forward frames only to the device specified in the frame's destination MAC address, which greatly reduces unnecessary traffic. Routers are truly network layer devices that forward packets from one logical segment to another. Gateways are simply translation devices that can work at any layer to provide integration between different technologies. A firewall is a fundamental security device that normally provides logical segregation between an untrusted network and a trusted network. The four flavors of firewalls are 1. Packet filtering, 2. Application level proxy, 3. Circuit level proxy, and 4. Stateful inspection. Packet filtering firewalls are nothing more than routers with access control lists to control the flow of traffic across the router based on source and destination values or protocol types. Packet filtering firewalls are the most prevalent types of firewalls implemented, but have limited security. Application-level proxy firewalls provide the most granular control, which gives the security professional greater security options. Circuit-level proxy firewalls make decisions about the flow of traffic based on the same criteria as packet filtering firewalls, but breaks the connection between networks because they make copies of the packets instead of forwarding the originals. Stateful inspection firewalls will track conversations between hosts on the connected networks to prevent potential malicious attacks. Section 4. Network Communications. Let me take you back a few decades to the mid-1980s when dial-up was the main way to connect to the enterprise from a remote location. A primitive solution to control the dial-up connection was called the Serial Line Internet Protocol, or SLIP. SLIP gave way to the Point-to-Point Protocol, PPP, due to a number of reasons. Among them was the fact that SLIP only supported clear text authentication. Not good. PPP supported protected authentication through the Password Authentication Protocol, PAP, the Challenge Handshake Authentication Protocol, CHAP, or more recently, the Extensible Authentication Protocol, EAP. Today, remote network connectivity can be achieved through more advanced metropolitan area network and wide area network technologies. For metropolitan area networks, technologies like fiber distributed data interface, copper distributed data interface, and synchronous optical network can be implemented. Wide area networks can be implemented as circuit switch networks or packet switch networks. Circuit switch networks tend to be more secure and more reliable, but expensive. Thus, most database networks, unlike voice networks, are implemented on packet switch technologies. The exception to this is Voice over IP, or VoIP, which takes advantage of connection-oriented packet switch technologies. For security, virtual private network (VPN) technologies like IPsec, Layer 2 Tunneling Protocol (L2TP), and Point-to-Point Tunneling Protocol (PPTP) can be implemented across packet switch networks. This concludes the preview of the telecommunications and network security domain of the ISC² CISSP CBK.